I'll start by talking about Source Network Address Translation, or NAT, then talk about Destination NAT, IP masquerading, some issues with NAT, and the idea of NAT and IPv6 together. So I should go ahead and point out that NAT is primarily used with IPv4, and I'll talk more about why that is in a few minutes. So the idea of network address translation is it enables us to remap an IP address from one address space to another address space. Used by itself, NAT typically refers to source NAT, which is sometimes abbreviated SNAT for explicitness. And what source NAT does is it transparently changes the source IP address of an outgoing packet to make it appear as though it's coming from the NAT device, and it tracks the connections associated with that outgoing packet and changes the destination IP addresses of any reply packets received to the address of the original sender. So in this diagram, it's a little bit easier to explain why we use source NAT. Here, what I have is a pretty common setup. I have a system on a private LAN, so this is behind a router that can do NAT, and this system has a private IP address. So in this case, 192.168.1.2. And this system is plugged in with a cable or perhaps connected wirelessly to a local area network. That local area network has a NAT router at its edge, so we call this an edge router. And it has an address on the local area network, in this case 192.168.1.1, and it has a second network interface in it, so the router has two network interface cards. The second interface is what we would typically call the WAN side interface, or the wide area network side. This is typically the internet, but not always. And we have a public IP address here, 203.0.113.1. Now this isn't a real public IP address, this is actually a reserved IP range used for documentation, but we're going to pretend like this is a public IP. And somewhere out there on the internet is a server with the IP address of 203.0.113.2, and our system on our private LAN behind the NAT router wants to connect to this server. Alright, so we want to make a connection to the server. So the system on the private LAN is going to, the application that's going to make the connection, is going to use a network socket to talk to the networking stack on that system, and a packet is going to be generated at layer 3 at the network layer, and that packet is going to contain whatever the payload is that we want to send. It's going to have a source address of 192.168.1.2, that's the address of the system, and it's going to have the destination address of this server, this 203.0.113.2 address. Now, to get from this system to the router, we're actually going to traverse down the OSI model, so we're going to traverse down the stack, get the packet packed into some data link layer frames, those frames put into a stream of bits sent out over the physical layer, arriving at the NAT router, where the packet is going to be re-extracted by breaking the bit sequence back up into frames and then extracting the packet from the frames. What the NAT router next has to do is it has to change the source address of the packet from this private address 192.168.1.2 to the NAT router's public address, this 203.0.113.1. And so what the NAT router does is it actually rewrites the source address of the packet, this is why we call it source NAT, from the private IP address to the public IP. Now technically we can have NAT between two private IP networks, and we could even do it between two public IP networks. NAT between two private IP networks is far more common, however. I don't know of any cases in practice where we would actually have NAT between two public networks, but it is at least technically possible to do it. Not really feasible or practical, but possible. So we rewrite that source address to the public IP of the NAT router. That gets sent out over the wide area network. You could imagine that being the internet. And that packet will arrive at the server. So the server sees that packet, it passes that packet up through its network stack to some server application that processes the payload of that packet and sends some sort of reply. Okay, and in this case, for simplicity, we're going to assume the reply is a single packet as well. And that reply packet is going to have the source address of the server, in this case, the public 203.0.113.2 address, but it's going to send the reply to the NAT router. So it's going to send it to the NAT router's public address, 203.0.113.1. Now, a big key in how this works is the NAT router remembers that it sent this packet from 192.168.1.2 over to this server, this 203.0.113.2. So when this reply packet shows up at the NAT router looks up in a table of state information that it keeps and says, oh, okay, yes, I sent this packet out for 192.168.1.2, and I rewrote it. I did source NAT, rewrote its source address to go out over the internet. So this must be a reply associated with that original packet. So what the NAT router does is it changes the destination address from its private interface, or its public interface, to the address of the private interface on the machine that originally initiated the connection. So it's going to rewrite the destination address on the reply to 192.168.1.2, and it's going to send that packet back over the LAN back to the system, and the system will get a response. So this is how source NAT works. Source NAT is an extremely common form of NAT, and in fact, your home router is doing source NAT in order to have your private IP range internally to your network be available to route out to the internet. Now, there is an inverse of source NAT called destination NAT, or DNAT for short. Destination NAT transparently changes the destination IP address of an incoming packet and sends that incoming packet to another device. This is typically called port forwarding, especially on small office and home office network equipment. And what this does is it'll actually do connection tracking, and it will change the source IP address of any replies to DNAT packets from the source address of the private side device to that of the actual DNAT system. And if all the ports are forwarded to a system, so if we take all our incoming traffic and we use DNAT to forward it to a specific system or a group of systems, we call that set of systems that we forward those packets to a demilitarized zone, or a DMZ, because those machines are effectively outside of the firewall that this NAT device is providing. Now, many SOHO type routers do source NAT. They also do destination NAT if you turn that feature on. So let's look at how destination NAT works. We have exactly the same setup here. So we have our server now, which I've colored in orange, is behind the NAT router, and it has that private address, the 192.168.1.2. And now we have a client out here somewhere on the wide area network or the internet with its public IP address. And we have the NAT router with its two network interfaces sitting in between. This is going to work in sort of the opposite direction of source NAT. So in this case, the client is actually going to send the first packet. And its source is going to be the client's public IP address with a destination of the NAT router itself, and there'll be a given port number as part of the connection. So in this case, we're using port 80, which is for regular unencrypted HTTP. So the packet is then going to go across the WAN, and it's going to arrive at the NAT router. Now, assuming the NAT router is set up for DNAT, and assuming it's set up to forward packets coming in on port 80 to this server, what the NAT router is going to do is it's going to rewrite the destination address of this packet to the private IP address of the server on the LAN. It leaves the source address alone so that the private IP address, the private server here, knows which client sent it this packet. So the server is going to handle the request, and it's going to send a response, which will get encoded into one or more reply packets. And initially, the source on the reply packet will be 192.168.1.2 because it's coming from this server and going out to this public client. So what the NAT router has to do, the DNAT, is it effectively has to do the equivalent of a source NAT translation now and change the source address back to the WAN address of the router. And then the packet will get sent on to the client. So this is kind of a simple case of how we can do source NAT and destination NAT when we have one device behind the NAT router. Typically, though, we're going to have many devices behind the NAT router. And when we have that situation, we have what's called IP masquerading. And the idea behind IP masquerading is that we can hide an entire private LAN using private IP addresses behind a NAT router that actually manages all the connections to another network. So all the traffic from every single device behind the NAT router appears to originate from the NAT router itself. And the NAT router will typically implement source NAT. Most of them will also implement destination NAT if the user chooses to enable those features. The reason why we do this is because it enables us to continue to use IP version 4. IP version 4 with its 32-bit address space is quite literally out of public addresses. In some regions of the world, there are no more IPv4 addresses to hand out. So what we do is we have a bunch of systems that have private IP addresses, we put them behind NAT routers, and that way we can have many systems sharing one public IP address. As you might expect, though, this does cause some issues. So when you're masquerading an entire network behind a NAT, that creates some problems with the protocols because a lot of network protocols are designed to be end-to-end. They're not designed to have their headers, port numbers, and other information changed while the packets are in flight. So there are some workarounds that can be implemented. One way is by adding more features to the NAT device itself, so adding application-level firewalls that actually work at layer 7 and know how to handle different common network applications. Or by making the applications themselves NAT aware and make them so that they can adjust themselves to the NAT environment. And one way that this is possible is using something called Session Traversal Utilities for NAT, or the STUN protocol. Now, as I mentioned, behind a NAT router, we normally, not always, but 99.9999999% of the time, are going to have a private LAN. And typically, the NAT router is going to masquerade this entire private LAN. So that means it's going to operate in one of the private address spaces for IPv4, which is 10.0.0.0/8, 172.16.0.0/12, and 192.168.0.0/16. So every single device behind the NAT router has to have a unique IP address. And that unique IP address is either going to be statically set per device or dynamically assigned. And for NAT routers that come as part of SOHO router appliances, a DHCP server is one of the components that will be running in that private network to hand out leases on IPv4 addresses on a temporary basis, so to be done dynamically. Now, I mention this because NAT is primarily used with IPv4. IPv6, one of its goals, one of the reasons for choosing a 128-bit addressing scheme, was to make it possible to restore end-to-end connectivity with every device given its own globally unique IP version 6 address. We have so many of these addresses that we really don't have to have NAT and hide things behind private address spaces, hide things behind routers, deal with stun, deal with all of these NAT traversal issues. That said, there is a simpler method of stateless IPv6 network prefix translation, which is somewhat similar to NAT, but it's much simpler and much easier to implement and causes many fewer problems with the protocols, although it is still an experimental RFC 6296 as of September 2017 when I made this video. The benefit to this particular idea, though, this particular protocol, is that a device behind an RFC 6296 router doesn't have to be reconfigured if the public network of the router changes. So in IPv6, the first 64 bits of the address are the address of the network, and then the last 64 are typically used for the host. So if, for example, a company or a small office or a home consumer wants to change internet service providers without using something like the 6296 prefix translation, what ends up happening is that all of the devices have to be reconfigured with new IP addresses with that new network prefix component. So there are some ideas from NAT that are useful that are being carried forward in active development on IPv6, but typically IPv6 is designed to obviate the need for NAT, and so we don't generally use it with IPv6.